you. Thank you. Can we predict who will develop colon cancer? I have an important story to tell you. There are two classes of people, those who will never get colon cancer and those who might get colon cancer if they live long enough. But we don't yet know how to distinguish between these two classes of people. How do I know this? Let me explain. First, I have to start with a man named Weibull. Weibull developed what's known as an extreme value distribution. An extreme value distribution characterizes the first or last occurrence of something. Let me give an example. Suppose you have a 100-meter race at all 25,000 high schools in the United States. In these races, all the students in the high school run, and their finishing times are recorded. You end up with about 18 million 100-meter times, and these are grouped into 25,000 races. If you plot a histogram for the average time for each of the 25,000 races, you'll get something like this. This is a normal distribution. It has the shape of the familiar bell curve. If instead you plot a histogram of the winning time for each of the 25,000 races, you would get something like this. This is a Weibull distribution. Note the difference. This is the Weibull distribution. I've written it here as y is equal to a function of t, where it's got three parameters, a, k, and lambda. Here's a graph of the function where I've got y as a function of t, and there's the Weibull distribution, there's a, k, and lambda. And as I change the values for a, you can see that it changes the overall scale of the blue curve, k, and lambda affects it by moving it to the left and to the right. At all times this integral, the area under this blue curve, will equal a. What does this have to do with cancer? Well, through years of research, we know some basic facts about how colon cancers develop. A tumor starts from a single cell. Many such cells exist in the colon. There's nothing special about that single cell. A tumor will be diagnosed shortly after the first of these potential cancer progenitor cells accumulates a particular set of mutations to its DNA. We can think of the tumor development process in the body as being like the 100-meter race. Different cells in the colon slowly accumulate mutations. When one has developed a sufficient set of mutations, a diagnosis of colon cancer soon follows. If we make a histogram of the age at which people develop colon cancer, it should have the same shape as the one for first place in the 100-meter race. The time for a person to develop a tumor is equivalent to the fastest time in the high school in the 100-meter race. A person is the equivalent of the high school, and a cell is just like a student in the high school. Now let's go back to the 100-meter races. One can determine the total number of schools participating in this experiment by integrating under the blue curve. In this case, the area under the curve is equal to 25,000. Now what if I told you that we cannot have all the 100-meter race data? I'm withholding any times greater than 11.5 seconds, so your data looks like this. Could we still estimate the number of schools? Yes, of course, because we know the shape of the curve and we could extrapolate from the data given to infer the hidden data. Like this. In humans, we have a truncated data set. Not many people live beyond 84 years of age. In fact, statistics are usually only gathered up to 84. So this is what it looks like. Here's some example data. First, you'll notice that the data is noisy. And in fact, the way I've made this example, the data changes slightly due to the noise. The yellow points do not all fall on a smooth line. This is how real age-specific incidence data appears. Now what we want to do is find a set of three parameters that provide the best fit to the data. You can see that by changing these parameters, I can get closer to a line that might represent the underlying data. You can see that all the yellow data points do not lie directly on the line. That is due to the noise. In this example, I can reduce the noise to a very small level, and you can see that the data points do fall on the line. From this curve, we can make a specific prediction about the values we should observe between 75 and 100. And the prediction is that the values would fall on this line. Here's some real data. This is called age-specific incidence data for colon carcinoma. It charts the number of diagnosed colon carcinoma cases as a function of age. The number of cases is divided by the population at that age. This corrects for changes in population as a function of age. The measurement is indicated by the yellow circle. The small lines attached to the circles indicate 95% confidence levels in the measurements. These are an indication of the noise level of the data. If I try to find the best Weibull curve by allowing all three parameters to vary, I get this red curve. The parameters of the red curve suggest that only about 20% of the population will ever get colon cancer. But what if we are so sure of the fact that colon cancer is inevitable? And we fix the first parameter to be 100% of the population and only allow the other two to vary. We get something like this. This green curve appears to be a slightly worse fit to the data, but the data do not convincingly reject this. Therefore, the hypothesis that colon cancer is inevitable in 100% of the population is still perhaps acceptable. Let's look at the two curves together. Note that they are similar up until 85 years of age. Then they diverge. If we could only get measurements for the ages of 85 to 100, we could clearly tell the difference. Wait, of course, there are plenty of people who live beyond 84 years of age. For some reason, these numbers are not typically released with the age-specific incidence data. I had to dig out the numbers of diagnosed colon cancers and population levels to derive this data. Here's what I found for ages 85 to 100. The 85 to 100-year-old data clearly falls on the red curve, not the green curve, indicating that not everyone will develop colon cancer if they live long enough. Let me summarize. We have a basic understanding of how colon cancers progress. They start in a single cell. Many such single cells exist in every person. Colon cancer is diagnosed when the first of these many develop a certain set of genetic alterations. This suggested that the age-specific incidence data should follow a Weibull distribution. It did. The Weibull distribution made a prediction about the age-specific incidence data from ages 85 to 100. We checked it. The data was consistent with this prediction. Therefore, we can say with great certainty that only a small fraction of the population is capable of developing colon cancer. The implications of this are profound. Someday, a test will exist that can notify you at an early age whether you need to worry about colon cancer or not. We just need to figure out what to test. Thank you.